So I'm going to spend a lot of time down here in the chair and whatnot, simply because I don't want to stand in front of the board and black you out. There's only one thing that I didn't actually do the math on, and that's going to be a big superposition problem, simply because you guys should know how to do superposition. I'm not going to go into all that. I'm going to do one small problem over here that I haven't completed yet, and that's all remnants from the other day. That's left over from Friday, so we don't need to see that just yet. That's not a big deal. Let's see. Yeah, now that one was a 5, and that one was a 10. There. That's that. And I think everything else is pretty much there. Yeah. Okay. So let's start up here as far as charges. What do you need to know on 17? You had to know what was the charge behaviors. First of all, you got to know that opposites attract and likes repel. And it doesn't matter if it's negative, negative, or positive, positive. Mass of the charge, you don't really, I'm not going to hold you to the masses of the charges. That's just silly. That's a wasted number. What you do need to know is that a proton outweighs an electron by a magnitude of 3 at least. Okay, they're thousands of times more massive. I am not going to do gravitational problems, and that's really the only time that you're going to run into something like that, is when you're going to try to conflict or put against the electric force to the gravitational force. And I'm not going to do that to you. There's two charges. There's positives and negatives. They are quantized. Now, what do I mean by quantized? This was in your book, and it showed the little Millikan oil drop experiment. Okay, E is the charge. Small e, lowercase e, is the charge of a proton and an electron. Okay, neutrons don't have a charge. So E, little e. Now, little e, take a bunch of them, electrons or protons, 6.2 times 10 to the 18th number of electrons or protons will give you 1 coulomb of charge. Now, if it's electrons, that means it's going to be a negative coulomb. If it's going to be protons, then it's a positive coulomb. Now, all E's must be whole numbers. You can't have 0.5 E. You can have 0.5 coulomb, but you cannot have half of an electron or half of a proton. But you can't have half of a coulomb. You just change that number in half. When it comes to these, conserve the whole number. They're not created. Everything is exchanged. Everything is exchanged. Electrons move. Protons do not. Protons never, ever, ever move. The only time that you could ever say that a proton moves is if you were talking about hydrogen. And that's going to be the ionized state of hydrogen. But hydrogen by itself is just a proton. It usually ditches that electron, so yeah, they say it's a proton. It's really hydrogen, or it's hydrogen that's cracked as a proton. Now, because of that, we get these two things up here, conductors and insulators. Now, notice I only wrote conductors. That's because conductors versus insulators. Everything is a conductor. Everything in the universe is a conductor, given enough voltage. The difference between a conductor and an insulator is the word easily. Okay? Wood, by and large, is considered an insulator. Okay? Conducts energy poorly. You got wooden tongs at home for the barbecue. They put wood on it, on the handles and everything else, because it doesn't do it well. Now, if you go outside during a thunderstorm and stand underneath the tree, and that tree gets struck by lightning, that tree is going to conduct that electricity quite well, and you're going to die. Now, will the tree fight it? Absolutely. Will the tree get burnt? Yes. Its resistance is high, but you can shove enough electricity through it that it will conduct. That's why the key here is easily. And when we're conducting electricity, what we're doing is we are actually moving electrons from here to there. Electricity is a mechanical process. At the end of the day, it's moving electrons from here to there. It is not math. It is not concept. It's not a plus and a minus. It's a freaking thing that moves from here to here. Now, if it moves from here to here, not a lot going on. It moves from here to here. Okay, now we've got some potential energy issues going on. We'll talk about that after a bit. All right, now we're going to make charged items because there are charged items. The first type is polarization. Let's say contact. Contact. We'll start with contact. Now, in contact, what you start out with is a neutral item plus a neutral item equals charged items. You rub them on each other. You had a problem in your homework that you should have done about jeans, denim, and a balloon. You rub the two together, and I think the balloon gains a charge of 4 coulombs, and the jeans says what charge is on that? Well, it's a -4. Because the balloon, if it got 4, then and they both started out neutral, that means electrons moved from the balloon to the denim. Again, mechanical process. They didn't come out of thin air, they came from somewhere. So, contact is the most basic. You just rub two things together and they rub off on each other. So neutral plus neutral equals charge. Polarization is temporary. Polarization, they do not touch. They can. It can lead to touching. But polarization, the act of polarizing something, is using the repulsive force of electrons against themselves. So what you get is a neutral and a charged item. I think your book uses a wall, and that's what most everybody does. This wall was neutral, or is neutral. You live in a neutral world, by the way. Everything's neutral. Why? Because you live on the earth. The earth is really big. And you're not walking around getting shocked all the time. That's how you know you're not in a charged world. So what you do is you come over here with a charged item. You bring the charged item within proximity of the wall. As you move it closer, the force from these electrons, the negative force, is going to drive these electrons away. Now, it will not draw the protons over. Okay, it's a solid. Now, in doing this, what you've done is you've created a temporary positive here for this negative. So you can take your balloon and you can touch it, and it will stick for a short period of time, and then eventually, it's not that the protons move over here, these electrons move over here until finally it reaches a neutral state. And then the balloon will fall down. Okay? Now, if you don't leave it up there for an extended period of time, and you put it back over here, these electrons will return. Temporary. You did not make a permanently charged item. You merely rearrange its negatives for a short period of time. Polarization. All right. Last one is induction. Induction is a permanent state. You are actually creating a charged item, and it will stay charged. So first thing you got to have is a charged item, and then you start with another neutral item. I want to go positive, negative, positive, negative, positive. Now, magnitude of the number of electrons I have here and there, negligible. It doesn't matter. I'm just drawing lines and filling up circles. So, what you got here is a neutral item. So I think I wrote up there. Did I? Yeah, charged and neutral. Yeah, cool. So, charged and neutral. Now, could this be positive? Absolutely, it can be positive. I just like doing this because it saves me time just writing lines. Okay? So, I got a negative item, and I've got a neutral item. As I bring this closer, we're going to see polarization occur. All the electrons are going to be shoved to this side, and I already drew them that way, right? Those electrons are going to try to get as far away as possible from these electrons. Now, induction involves this. A conducting wire to this symbol. And this symbol means ground, which means that wire is attached to the earth. The earth is what we call a reservoir. It is willing to accept as many electrons as you want to give it. It was willing to give you as many electrons as you want it to give you. It doesn't matter. The earth does not have a charge. This passing between you and it is not going to create an imbalance of electrons, because whatever you take, somebody else is giving up. Whatever somebody else is giving up, you're taking. Whatever. Okay? So, the grounding. So, you take your charged item, you bring it close. Don't touch. Don't touch. Bring it close. The electrons will move as far away as possible. Now, if you have a conducting wire, they can leave. They can go down this wire and they say, oh, I'm getting farther, 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 farther away, till finally they end up in earth. Cut the wire. Remove Move this, move it away, you now have two charged items. And it's permanently charged. Or until you touch something where you can get its electrons back. Okay? Has anybody ever heard of a grounding wire? Like get a car or an electron and say, hey, it's grounded. It means you're allowing electrons to pass up and down. If your electric system is not grounded, it's not going to work. So that symbol right there means ground. And then if you wanted to do it the opposite way, let's say that this was incredibly positive and this was neutral. Okay? If the wire is there and I bring it close, positive, 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 bunch positives, that means it's going to attract extra electrons trying to balance that out. You cut the wire, move that away. Now this thing has more electrons than it has protons. Now we have a negative charge item that we can then take and then screw with something else. Okay. All right. Is everybody good on that stuff?
Yes, sir.
Excellent. Let's move down to Coulomb's law. Do you need to know what Coulomb's law is? Yes. It's not up there because by this point you should be able to do Coulomb's law. Kc, Q1, Q2, absolute value, R squared. All right? All right, so I'm not going to write that. Now, what you do need to understand is that it's always going to be absolute value and there's no direction. There is no direction. Okay? What you are figuring out is the force between two items. And it's only two charges. You're figuring out the force in the system. That's it. The force, not direction. Why is it not direction? Okay, well, let's look at this first. Here's Coulomb's law. Here's my situation. I got a -5 and I got a 4. Right? Here, charge 1, charge 2. Here's my distance. Let's call it 37 centimeters. I put it into Coulomb's law. And I find out that it's 1.31 times 10 to the 4th newtons of force between these two. What I've just found out is that if I magically lock this one in place and this one in place, they can't move. If I let this one go, this one is going to move towards this, which would be in a negative direction, because this is negative, that's positive, with that much force. If instead I lock this one in place and let this one go, this is going to move in a positive direction with this much force. Coulomb's law does not give you direction. All it does is give you force. The direction comes from you understanding the system and saying, I am talking about the number 4 charge or I am talking about the number 5 charge. That's all Coulomb's law does for you. Okay? So force electric is repulsive or attractive. Force due to gravity is always downward. Now, when you have downward force, the only time that you ever get the quote unquote floating is when force due to electric, which would be your static electricity, versus gravity. That's the only time that those two are ever going to be, and it's going to be in a dead vertical situation. And I'm not going to do that to you on the test. But you need to understand that this is a balance between two field forces. That's what you need to take away from that. Okay? Now, I use the word floating because this also occurs when you're in a fluid system. And we are going to be doing Archimedes' principle later on. So you need to understand the idea that that force electric is going, up, and then that's pulling down or whatever. These two are balanced. And we ran into this also when we did spring constant. The same idea. All right. Equilibrium. When it comes to equilibrium, you got a system. You've got two items that are already there. And in this case, my problem here, I wrote 2 to the -6, 3 to the -6. Question is, where does a 17 to the 12th go? Now, when it comes to equilibrium problems, they are always going to both be negative or both be positive. You cannot have a negative and a positive. It doesn't work. Okay, if it's a negative and a positive, that charge is going to do something. That's a negative and that's a positive and that's a positive. I can tell you right now where that charge is going. Way over here. It's being attracted and it's being pushed. So it's always going to be 2 negatives or 2 positives. That light bulb hadn't come on, now you don't have to figure that out. Okay? Now, do I care if they are negative or positive?
No.
No. If they're both negative, you know what? I don't like negative math. I don't care. Drop the negatives. You're going to get the same result. Because they're either going to pull on each other or push on each other. Remember Coulomb's law? Right? All you're doing is Coulomb's law. and it's nothing but force. So I don't care about the magnitude of the charge. I mean, not the magnitude, but the positive or negative nature of the charge. So in this case, I got this situation. I got a charge, got a charge, got a charge. I got 3 meters. Now, step one. Pick a team. Pick a charge. I don't care what charge it is. Left one, right one, doesn't matter. But pick a charge. I usually pick this left charge to be D, and then this right-hand charge is going to be 3 minus D. How do I get 3 minus D? It's 3, whatever this distance is whatever's left after I subtract this distance. So 3 minus D. Okay? Pick a team, write it down. Don't put it in your calculator and go to town. Write this stuff down. So when I write it down, I write down the Coulomb's law. So I got Coulomb's law, I got Coulomb's law. Notice the equal sign, because that's the whole point of finding the equilibrium point. Is it going to be here or is it here? Where will this thing find equal force from the 2 charges? Now, the beauty is, since they're equal to each other, you start killing the problem, start killing pieces, parts out of it. We can drop that out, we can drop that out, we can drop the 17 out because it's on both sides, and technically you should be able to drop out the -6. I hate doing that just because it seems like I'm really dropping out a lot of stuff. So I usually carry that one through, and as you can see here, once you drop everything out that occurs on both sides, this problem gets really, really simple. You cross multiply, so we get this. Square root it all. Square root it all. Why do we square root? To get rid of these squares. Okay? Don't do the math. Simplify it. Then, once you've got the math, so this is the square root of that, that's the square root of that. Notice the -3 and -6, -3 and -6. Okay? Now, multiply all the way through. So that times that, that times that, that times that, and that changes it to this. Okay? So 4.2 is 1.4 times 3. Done. There and there. Okay? Solve for D. You're back to doing basic algebra. This is multiplication, divide, D. D is, remember I said pick a team? That's why I always write it down. The D belongs to the 2 charge. 3 minus D belongs to the 3. I found D. And so my answer has to reflect 1.34 meters from charge 1, which is the 2 to the -6. Not only do you have to pick a team, but at the end you have to describe what happened. What did you do? And I found out that D, if I don't have this up here or a guide, I don't know which one's got D. So I have to say it. That's my label for those problems. Telling me which one is which. I want to make sure I don't miss anything in here.
Where's the 17 come from?
17.
Yeah.
Oh, right here.
Yeah.
That's the charge that I'm trying to find the equilibrium point for.
Gotcha.
Yeah, I provided it. Sorry, this was one of the first stuff I wrote, so I didn't know how much I had to squeeze in.
Good.
Let's see. Oh, definitely, and I forgot to mention that. Know the charge of the electron. Know the charge of E. That's why I wrote this stuff down. Okay, definitely know the charge of E. That way you can go either way, and it gives you charge. Position. Got that. Equilibrium. Got that. All right. Electric fields. When it comes to electric fields, they are 360-degree field forces. They are field forces. That's why we keep having that distance squared in thing. Okay? They drop off as a function of the distance squared. Just like energy. When we were doing the light labs, light drops off at a function of distance squared. Gravity drops off at a function of distance squared. So does electric force. Anytime you are dealing with a 360-degree sphere and you are increasing the distance, you're not producing new energy. That same amount of energy is being spread over a greater field. So it falls victim to distance squared. So it felt 360 degrees, capital E is the strength of the field. Now where does the strength of the field come from? It comes from the charge making the field. You got a big charge, it's going to make a strong field. Now when it comes to field forces, folks, One of the best ways to think about this stuff is gravity. I'll be real honest. You all understand gravity quite well. Everybody here, you grew up talking about gravity. You know that if you fall from a greater height, it's going to hurt more. Right? You understand that Jupiter has a greater gravity than Earth. You understand that the sun, you understand gravity. This is not a lot different than gravity. Okay, it's different terms, but the concepts work the same. All right, so let's talk about test charge. Test charge, number one, is always going to be positive. So when we talk about electric fields, it's always going to be in reference to a test charge. The test charge is always positive because somebody who decided that we're going to talk about electricity years ago said we got to pick a team. It's going to be positive, it's going to be negative. They picked positive for no reason whatsoever, which really seems rather counterintuitive to me. That's why I try to pound it home that they're talking about, when they say direction of an electric field, what direction would a positive charge move? Which seems stupid because what's the only thing that's allowed to move? Electrons. So it seems counterintuitive, but that's what it is. It is what it is. And we can't change the rules. This isn't open to interpretation. No, Mr. Gray said it works so much easier this way. No, I can't change the rules. Test charges are always positive. Okay? So when we talk about fields, electric fields, it's always in reference to what would a positive charge do in this field. Now, if you want to talk about a negative charge, well, you just got to reverse all your thinking. If you say a positive charge is going to move this way, cool. That means a negative is going to go that way. The key here is to remember that it's a positive charge when you're talking in reference. Which way does gravity work? Down. There. See? It's no different than that. Gravity always works in one direction. Things always fall. In this, positives always go that way. All right. And it's always incredibly, incredibly small. It's so small that it doesn't matter. You versus the earth. You jump up in the air. Bailey, you're my little basketball player. So that means you probably got some vertical height. So he jumps up 2 meters in the air. Yay, Mr. Bailey. Okay? Now, by all rights, he pulls up on the earth. Does everybody agree with that? Does he? No. You don't. Yeah, we like to think you do, and some minuscule nothingness. Yeah, sure, you moved the earth, buddy. But did you? Okay, that's the test charge. Now, we want it to be so incredibly small and insignificant that it doesn't screw up E. That's the idea. We don't want polarization to occur. Okay, so if we've got E, awesome. If we've got a charge, E, and it's got this field doing this, right? And we put another E over here, let's say this is just our charge, right? Well, it's really going to screw up these field lines, and we'll talk about field lines in a minute, but it's going to screw up all these nice parallel lines that are supposed to be coming out of this. Is that very good? That's why it's always incredibly small, and it's always going to be positive. Okay, or that's why it's always small. So it doesn't screw up the original electric field. And that was a really bad example because it's round, but E is always going to be parallel. All right, E at some distance. What force do you feel at some distance? There's your formula, folks. That's it. This is a plug and chug type moment, and a number of these are going to be plug and chugs. You guys have been working real hard on trying to figure stuff out. There ain't a whole lot to figure out. If you get the basic concepts, it's pretty easy. There's going to be key words that you just look for. Okay, I mean, really, that's what you're looking for, because there's only going to be one formula that actually works for it. All right? So if you want the strength at some distance in an electric field, okay, there it is. There's your electric field formula. There's your charge. There's the distance. And we all know what Coulomb's law is, right? So, when we do that, this is what we're dealing with up here. And this is the one problem I'm actually going to do. I'm going to walk you through this. All right, so let me clear this up real quick. That's 30 and that's 50 if I can remember all my numbers. So here's a charge. That's 2 to the negative 3. Yeah. And here's charge. Here's charge. This is 50 centimeters there. We'll move that up. And this one was 3 and then -6. 3 and -6. And I think they're both positive, right? Because I don't want to reinvent the wheel here. -2. All right. So, question is, what's going to happen to a test charge in this electric field? Now, obviously, here's my test charge right here. Maybe that's not obvious, but here's my test charge. They're going to give you at some point in this electric field. Now, this is an electric field being formed by this. Okay? This is forming an E, this is forming an E, this is an electric field. How much force does this charge right here, this test charge, feel at this point? Okay? Now, we can only deal with one charge at a time. Can't do coulombs, we can't say this and this and say here's the system. We gotta say here to here and then here to here. So that's where it comes in with, hey, they're asking me field strength at some point. There's your capital E. Right? So I have two charges. That means I gotta use the formula twice. Now when I look at this, first thing I always kind of do is go, okay, I know this is positive. I know this is positive. So a general idea in my head is, and I like drawing these pictures. Say, okay, this is a -2. That's a positive. That means this thing is going to be pulled down this way. And I like putting arrows on. Right? This one over here, this is a 3. That's a positive. That's a positive. So that means that dude is actually want to go that direction. Does everybody follow that idea? Right? So they're obviously going in two different directions. I got a 3. That's big. That's bigger than a 2. Excuse me, but I got 30 centimeters here, and now I got a hypotenuse of something here, right? So will this distance overpower or be less powerful than the magnitude of charge? Well, let's find out. First thing we got to do is we got to figure out this angle because we've got a triangle. We got to have this angle so we can figure out the hypotenuse of this right here, right? Because it's not an x and a y. So we go over here and say, okay, opposite over adjacent, tangent inverse. That's 30 degrees. So this angle right here is 30.96 degrees, right there. Now it's the same thing as what would be up here, right? Basic geometry. So hopefully I'm not teaching you that. And then I say, okay, well, I need the distance. 3 squared, 5 squared, square root, 0.58. It's 0.58 meters from here to here. So I do the math. I plug in the first one, I say, okay, what is the force felt between these two? The force is 2 times 10 to the 8th and 7.93 times 10 to the 4th. Just using that formula. Now, yeah. Oh, I thought you had a question. I'm sorry. All right, now, X and Y table. We got charge 1, we got charge 2. Charge 2, X and Y. Now, charge 1, I'm calling this charge 1, this is charge 2. So charge 1, does it have an X value when we're talking about the test charge? Remember, this is not moving, the test charge. For the test charge, it's not moving to the left, to the right, so the X is going to be 0, and the Y is going to come straight down. That's where my arrow comes in. That's going to be 2 times 10 to the 8th. Charge 2, on this one, we've got to do the sine and cosine. So, got my opposite, I got my adjacent, so you do your sine and cosine, and you find that those values are, for the X, for this portion, the X is negative 6.8 to the 4th, and 4.08 also to the 4th. Does anybody, I don't need to do the sine cosine, right? Everybody's familiar with that? Okay. Sorry, I have to put my glasses on, I can't see this stuff. All right, so I add these together. Negative 6.8. That added together is 6 point something, right? Negative 2 to the 8th. Negative 2 to the 8th. Yeah, because that's 8 and 4, so it's not just 6. So, I do that. That's my X, that's my Y. Notice it's a negative X, and it's a negative Y. Something like that. Everybody good? New triangle. And those should be to the 4th and to the 8th, so it's 4th and to the 8th. So that means it's not going to be very much X compared to that Y, right? To the 4th versus the 8th. Small magnitude, large magnitude, so it's going to do something like that. That means my particle, that test particle, is going to be shoved this way, but it's also going to be pulled a bunch this way. So what was stronger, the distance or the charge? What made the larger impact?
Charge.
Distance. Distance, by far. This is a 3 and that's a 2. And notice that this thing's getting dragged down, right? It's getting drugged down a whole lot more than it's getting shoved up and away. Does everybody follow that? Remember I told you distance squared? That's where that magnitude comes in. Okay? Because it falls off. It's field force. So, we got our new triangle, we got our new x, we got our new y. So we square it, and we get 4.62 to the 9th, and we get 4 to the 16th, and then we square root that, and we get 4 to the 16th again, yeah, because it's so the 9th and the 16th, so it's really magnitudes. And we end up with 2 to the 8th newtons. And then you do opposite over adjacent, you find out the angle, and it would be 2 to the 8th newtons, 89.98 degrees below negative x. Because it started here, and look at these numbers, right? So this thing barely goes over, it goes way down here. And the angle that we're finding is this 89, it's like, oh, it's this one right here. Opposite over, it's this one, it's like 89 degrees. Or 89 degrees, I'm sorry, right here. Yeah, 89, it's almost vertical. So that x value is virtually nothing. So again, what's more important, distance or magnitude? Distance. By far. By far. Okay. So field lines. Okay, let's talk about field lines. When it comes to field lines, here's my two charges. And there's a couple options when it comes to field lines. There's always going to be rules. Get rid of this real quick. And I'll draw some other examples. Got a negative 5 and a negative 10. Let's go positive 5, positive 10. Negative, negative, positive, positive, negative, positive. Yeah, okay, cool. All right. Now, number one, they always leave the positive, they always go to negative. Field lines always go positive to negative. Always go positive, negative. Now, why do they do that? Because, let's say we had a charge. Here's E. It's going to go like this, right? Now, why are my arrows going that way? Because if I was to drop in a positive charge next to this very positive E, which way is it going to go? Everybody follow? Remember, all discussions are in terms of a positive test charge. So if I had this situation and I dropped a test charge into this picture right here, where's that test charge going to go? Is it going to go screaming to the 5 or screaming to the 10? To the 10, because the positive charge, test charge is positive. Okay? Now, they never cross, and they are always proportional, or can be proportional. Now, I've got a couple options here when it comes to this 5 and 10. Does everyone realize that 10 is 2 times greater than 5, right? So I have option A. 1, 2, 3, 4, 5. And then, of course, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That works. Notice that I have 5 lines leaving. I have 10 lines coming in, right? And technically these would be more like this. That one would go there, because I can do that. That one would go there. That one would go there. So all 5 leave, all 5 arrive, yes? But notice how this is a pain in the butt. Okay? Positive, negative, never cross. Can't touch, no touch across the streams. Ghostbusters 101. That's a lot of arrows though. I don't want to draw that many arrows. I want to draw this many. Done. Notice that there are twice as many arrows coming into the negative as are leaving the positive, yes? It's a 2 to 1 ratio. 2 to 1. Proportional.
So you basically just divided both sides by 5.
Yeah. Because if this was, let's say this was a 24 and 8. Say this is 8 and this is 24.
Right. Divide both sides by 8.
Yeah.
So 3 to 1.
Yeah. Proportional. It works. Because all we're doing is showing the magnitude of the force. That's really all we're doing.
Right.
We're showing what would happen if you were to drop a positive in. So if it's 100 and 1,000, Okay, that's a 10 to 1. Okay? If it's 999 to 100, yeah, that's gonna suck. Because you can't even divide it by 2. So that would be a very crappy picture. All right, so we got a positive going into the negative. We got a negative into the negative. All right, comes in, comes in, comes in. 2 to 1. Positive to positive. Can't cross, right? Now I could have saved myself and said over here, but then I kind of need something to balance this out. And I can show, if I do it here and I do it here, I can show that these two are not going to be attached to each other. That's why I chose to do this rather than this. Because that kind of leaves this weird area right here. That might leave it to open to question or interpretation. This definitely says that anything coming out this side ain't going over there. So, negative, negative, positive, positive, negative, positive, and then if we just reverse these, obviously I hope, you're seeing the trend here. It would be, oh wait, that one, and then, let's see, leaves positive, yeah, I have to change that. That one would go there, and that one would go there. Because it can't come here. All right, field lines. Yes? Good? Awesome, awesome. So my daughter's coming back from Okeechobee. She had dance, when she goes to the music fest things. So she's coming back from, I apologize. Okeechobee, Florida. She drove all the way down there. Her and her girlfriend. Yeah, and they drove back. They left last night at 10 o'clock.
How old are they?
She's 22.
Spring break?
No. She took days off. She's not going to college. All right.
That's crazy.
Let's talk about potential energy. Woo-hoo. All right. Potential energy. Change of potential energy. First, we're going to talk about gravitational potential energy. Over here on the right-hand side, I have something that should be familiar to you all. All right? Potential energy, gravity. Now, everybody in this room should know what potential energy is, right? You got two kinds of energy. You got potential energy, you got kinetic energy. Potential energy is energy of position. Kinetic energy is energy of velocity or movement. If you have one, let's say you have potential and it starts moving, the potential energy drops, but the kinetic goes up. Okay? Now, how do we get potential energy? Gravitationally speaking, we say potential energy, gravity. If we want to figure it out, we say mass times gravity times height. And everybody in here understands what mass is, right? And you understand that if you hold this marker above his head at, let's say, 20 centimeters, and I drop it, it will do work on his hair. It will displace his hair, right? Because that potential energy turned into kinetic energy. Same marker, let's say I hold it at, 10 feet above his head. Yeah, I drop it. Now, it's got more energy, right? Now, if we negate air resistance, when it hits his head, it's going to do more than just move his hair. So let's get stupid with it. Let's take it a mile up. I drop this marker from a mile up, neglecting air resistance. Is he going to have a good day or a bad day? Bad day. Worse than a bad hair day, right? Because it's going to punch right through his little hair here and go into his skull because it has more potential energy, yes? Okay, now, what if instead of a marker, I drop, something like a paper clip? There's no way a paper clip could kill him unless I drop it from a mile up. If you get rid of air resistance, it's going to punch right into his little skull. Everybody follow? Okay, so everybody in here understands mass determines how much energy you have. Gravity, if we do the same experiment, if we go to the moon and I drop this, okay, I can drop it from a mile up. By the time it hits his head, it's not going that fast, right? Because it has less gravity.
Yeah.
So, we understand mass, we understand gravity, that's the field, and we understand height, which is a distance, yes? Okay, let's look at electrical potential energy, because it's the same thing. Q, right? And I'm going to get rid of this negative. Okay? First of all, don't look at that negative. Q. That's the charge. That's nothing more than mass. Right? Okay? E. Electric field. It's the same thing as freaking gravity. And the last one, distance. Everything is height. It's the same system, folks. Different terms, different things creating the fields, but the rules are the same. Now, let's talk about that negative. Potential energy, you change in potential energy, equals negative. Because, we have to go back to this. We're going to go back to the terms of a test charge. Here's E. E has arrows, and they go that way because if we drop in a test charge, let's say we dropped a positive test charge in right here, it's going to want to go this way. Does everybody agree with that? Here is the source of the electric field. Okay? Where does that want to be? Yeah, as far away as possible is from here, right? Okay. Again, equating this to gravitational energy. Here's my test rock. Where does my test rock want to be? Down here. If it goes the way it wants to go, it's actually, this may be potential energy, but by the time it gets down here, it's like, right? It lost a crap ton of potential energy, yes? All right? If I take a test charge and I move it in here and it wants to go and it goes from here to here, that's the same thing as taking this diagram and doing this, right?
Right.
So if my charge is positive, what happens to the amount of potential energy that it has? It decreases. See the negative sign up there? That's why the negative's there. If I have a positive charge and I put it in an electric field and I let it move, it's going to lose potential energy from this position versus that position. And it's going to have, this has greater potential energy than this. And if it has greater potential energy, then that means it's got more ability to do work if I let it go and go down here, because that potential energy is going to turn into kinetic energy, and if I put a drill bit down here, the electron slams into it, it'll spin it. We get work. Okay? Now, if I take a negative, right? Let's say I take a negative charge, and I move it from here to here. Where does the negative charge really want to be? Over here. Does everybody follow that idea? So if I move it from here, that's like moving it from here, right? And I move it up to here. So if I move it from here to here, that's, again, this diagram again. If I move it from here and I move it to here, it now gained electric potential energy. If I move it from here to here, it gained potential energy. Because I think everyone in here, we established negatives try to get to positives, yes? There you go. All right. Okay, potential energy, there's your formula right there. Potential energy in a system. Folks, it's no different, absolutely no different than Coulomb's law. Outside of the fact that you're actually using the real charges. It's not that absolute value stuff anymore. Yeah?
I thought potential energy, the R wasn't squared.
It's not. Good catch.
Good job, bud.
Now, folks, again, that's doing nothing more than trying to figure out how much potential is in a system between two charges. You lock them in place, how much work can you expect them to do? Now, that work, we kind of define that as volts. That's what it actually is, because that's your change in potential energy. Next one down. Volts is equal to change in potential energy per charge, based on the charge. The bigger the charge, the more work it can do. The bigger the rock, the more work it's going to do on Austin's head. In the same exact field. Now here's the kicker. If I drop an elephant, or I drop a marker, which one's going faster when it hits the ground? Neglecting air resistance. They're the same.
Once you said it.
So the E thing, that really just, that just accelerates everything, right? The E is accelerating everything. The mass, that's where you can get the difference changing, which in this case is the charge. The more electrons you move across, the more work you can expect. That's why it's based on charge. Yeah, gravity doesn't care how big you are. Pulls everything at the same speed. Neglecting your resistance. Battleship, same thing. I don't know how you lift a battleship. Whatever. All right. Now. Okay. Last one. Here's a key word. Infinity. See that how it says infinity? If you see a problem that says infinity, there's your formula. Now, it doesn't have two charges or anything like that because it's at infinity. So your distance becomes incredibly large, right? Infinite. So if you divide something into infinite sizes, it's going to be infinitely small. It's going to be so small that it doesn't matter. It's kind of like Bailey and his vertical versus the earth. All right. So there's your keys.
V is volts, right?
Yes, ma'am. We are out of velocity for now. My fancy V is now volts.
For a second I did think velocity.
I know, and that's okay.
Second semester final grade, that's gonna be tough. Remember in the first unit stuff?
Well,
Okay.
second semester final has nothing to do with first semester material. It's not a year-long final.
Wait, really?
Yes, second
Yeah,
semester
it's a
final.
second semester. That's why it's called second semester final.
I'm glad.
Okay.
Now you see.
Screw
Yeah.
cannons.
I don't know if you're necessarily do because we still have superposition, so we might,
Okay.
you might want to keep
I
that
like it
knowledge
better
around a
than
little bit.
cannons shooting stuff.
All right, here we go. Capacitance. All right, when it comes to capacitance, first of all, let's talk about what a capacitor is and what it means in our context. When we talk about capacitors, we are talking about double plate flat capacitors. Okay? We have a plate on this side, we have a plate on this side. In between those two plates, we have some type of material called a dielectric. Now, for you all in your homework, they keep saying the dielectric of the vacuum. So E sub 0 is the dielectric. You do not have to memorize those numbers. We have those on tables. It's kind of like when we were looking at index of refractions. Okay, they have a whole book for this stuff. And so you don't care about it other than, hey, give me the number to plug into the equation. That's as far as your concern needs to be. And you need to know that it's located there. Now, your basic capacitor has two plates. A is the area of a plate. And they're going to be matching plates. How big is the plate? And then D, for the formula, oh, that's in the hallway. I thought somebody had a really interesting ringtone. I don't know how you hear that driving your car, but whatever. All right, and then, so we got distance, and the distance is separating between the two plates. Now, what is a capacitor? A capacitor is a battery. And what happens is you've got one wire attached to this plate, one wire is attached to this plate. And as long as these two are attached, remember how the electrons always want to get to the positives? Right? Polarization idea? So the electrons will go down the wire and they will load up on this plate. This plate will just be full of electrons trying to get to this positive side. Now, it's not like it's a big bank of protons, it just doesn't have any electrons. Remember, electricity is nothing more than a charge is plus or minus electrons. You either have too many or you don't have enough. So these electrons are trying to get over here where there is less negativity. So what they do is they pile up on this side. And you hit a button, okay? And when you do that, you either do one of two things. You either bridge across the two plates, or it pushes the plates close enough together that they can arc. Okay? Now, you've all seen arcing. You walk around in the wintertime in your socks, and you walk up to a doorknob, and before you actually touch the doorknob, you see that little spark come out, right? Or you've built up, that's arcing. You've just got enough electrons on your fingers that the charge is great enough that the attraction, it'll just jump across. Has anybody ever seen lightning? Welcome to Mother Nature's capacitor. The sky is a plate. The ground is a plate.
Whoa.
The air is the dielectric. Now, as air moves up and down, it's like you walking across carpet. The electrons scrape off of each other. So we get an imbalance. Either too much up here or too much down here. Once it reaches a critical point, a weak point occurs, and it goes bam. That's lightning. It starts on the ground. It doesn't start in the air. It actually starts on the ground, and then it will both, and they try to find a path. It's like a giant maze.
What? I always see pictures of it coming down.
Is that why it's all jagged?
Yeah, because it's trying to find paths of least resistance.
Oh.
Yeah,
It's so dope.
yeah.
They're cool.
Well, it's really cool because you know you're gonna get struck by lightning, and this is a sidebar. But if you go outside, Robbie, your hair's long enough. Taylor, your hair's long enough. Yours probably is not, and yours isn't either. But if your hair starts standing up when you're outside, you are the plate.
Oh Lord. So if you jump up and down, would that work?
No, get down. Get down. Touch the ground. Because the ground, you're the plate. That means you've got either not enough electrons or too many. Touch the ground.
Oh.
Because the ground will give you or take away electrons.
Yes.
But that's what you actually can. They've got pictures of people, and it's really unfortunate pictures. Where people are like, dude, check out my. And it usually films, you know, like, hey, check this is really old. Damn, sorry. All right, now, that's bad stuff. Now, what do we use these for? Flashes. Not in your phones anymore, but they might actually have, yeah, they got capacitors in them. Because what they'll do is they will build up a charge. It takes too many electrons to make that flash in one time. Your batteries aren't designed for that. Your systems aren't designed for that. But what they'll do is they will say, okay, here's our little bitty phone battery, and it'll light up this plate, and then it'll say, okay, when you hit flash, it connects the dot, and that big arc is just basically energizing the light bulb for a split second. It goes off. Okay? If you've ever used it, has anybody ever used a disposable camera?
Yeah.
Okay? And you have to hold the button and wait for it to blink red or blink green or something like that? Okay. It's the exact same thing as a defibrillator. Okay? You've seen movies where people have a heart attack and they pull out the paddles and they stick them on there, right?
Yeah.
Oh, they do this because it's got lube on it so they get a good contact. That's honestly why they do that. And then they'll go, okay, they'll set it up, they'll get the cables and say, all right, charging, 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 charging.
Ding.
It's actually setting a charge on a paddle, right? The other one doesn't have a charge. It's just connected to the positive. And then they put it on the person. As soon as they put it on a person, right before they pull the trigger, what do they always yell?
Clear.
Clear. Because what are they getting ready to send through their heart? That's why they put it here. Yeah. A massive electric charge. Then they're jump starting their heart. They're literally jump starting their heart, just like a car. Now, if you are dumb enough, and I get it, you're a concerned citizen and you see your friend who's dead, because they're dead. That's why you're using defib. That's why they're, you're not doing this on a live person. Okay? They're dead. So, and that's why they also say, hey, if you see somebody, grab the deep, they got instructions. You can't make them more dead.
True.
The best you can do is save their life. So, the thing is, though, people will go, oh my gosh, Johnny, Grandpa, you gotta hold him, don't hold Grandpa. Do not hold, he's dead. Okay? If he wakes up with a bump on the back of his head because he flopped like a fish, but his heart kicked on, good for Grandpa. Because if you're touching Grandpa, when they send massive amounts of electricity through him, guess what?
You die.
It can kill you. It might save Grandpa, but you will get hit. And it might kill you.
And then they switch and then
Oh, what's the nephew? Me and Grandpa going down. I'm not really there yet, okay?
Yeah, I'm good, Grandma.
Yeah. Grandpa loved you, but you had a good life.
You've been here longer than me, Grandma.
All right? I know that's a terrible thing to say, but it's true. Here it is. Defibrillators, same way. You got a paddle, you got a paddle. You got a charge. And now, once this thing discharges, you got to give it time. And that's why when they hit people with the paddles in the real world, they'll say, okay, charging, 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 charging. And they'll hit them again. And then they'll hit them again. because this has to build up those electrons. I know this isn't real familiar anymore, but you guys grew up with big TVs, thick TVs, right? Okay, yeah, they have tubes, right? Here's the thing, your wall outlet does not provide enough electrons to kick that thing on. Flat screens take almost no energy whatsoever. They're very economic. I mean, outside of the heavy metals and stuff that are in them, I mean, they're actually not that bad. The monitors don't take that much, but the old boxes, this will not power one. It can maintain it, but it can't start one. So when you would turn on your TV, you would hear that boom. It's that thing going off. And then it would go off, jump start your TV, and then you're watching TV, and while you're watching your TV, it recharges the plate so that when you turn it off, if you want to turn it on again, it can turn it on again. Now, that's why you don't open these old TVs, because there's enough electricity, it's greater than 110 volts.
What if you
Right?
smash it with a hammer?
If you make contact with those two plates, then you just turned your TV into a defibrillator, and we've established what happens when you hit defib when you're alive. Yeah, dong the. But on the plus side, we can hit you with defib now. You can't get less more dead. Doesn't matter. Doesn't matter. It can be sitting in your grandparents' basement for the last 10 years. It's charged. You don't play with TVs. Okay? All right. Yeah, we're up.
So, like, say you're defibrillating on a person and they wake up, and then you accidentally give them another hit.
Trust me, you won't, because if they wake up, it takes more than just a second for that thing to recharge. It takes about 20, 30 seconds. So
you
you've got more than enough time to see whether or not they're responsive. Yeah. Yeah. Accidents, you don't accidentally hit somebody with a defib.
I'm pretty sure defibrillators have like a heart sense.
And then most of them, because they don't want you killing somebody. Grandpa's not breathing, he's just, you got drunk, leave him alone. All right, so, over here, when it comes to capacitance, now this formula right here, this is the basic definition of capacitance. Now, I say that because this is the definition. This definition can be substituted into other things. Okay, it's a definition. So I can't tell you there's a particular time when you do this. Unless, of course, they say, okay, here's your voltage, here's your capacitance, what's the charge on the plates? That could be it, but it might be other times you gotta use it. But that's a definition. This is the formula for a particular capacitor. Okay? And then down here, when it comes to potential energy, here is your keyword. When you want potential energy in a capacitor, one of these three forms will get it done. And that's all that's all these three are. Now, if you read your book, they had one of these, I can't even remember which one. One of them is actually in a box. But then the other two, they're just in the reading. So here they are. So when you see potential energy in a capacitor, there's your three formulas. Now, if you got charge and you got voltage, cool. Then you can find, potential energy. If you got capacitance and voltage, cool. You can find potential energy. If you got charge and capacitance, no voltage, that's cool. You still find potential energy. Okay, they're all just variants of the same idea for potential energy. And the math's been done for you. If you want to see the math, good for you. Look, it's at like the last page of chapter 18. It's on the back side, and it's got a little spider web like of lightning. Okay? But it's in the reading, it's not in a box. That's why I included it in this. Everybody good?
Sorry.
All right, folks. I'm done.